Good afternoon. Welcome to this PE review session on hydraulics. The topics we'll talk about today are listed on this slide. First, I'll review some basic variables and units that we traditionally use in the field of hydraulics. And also, today's session will cover both pipe hydraulics as well as a little bit of open channels, primarily intended for the audience who are taking the morning session. And of course, I'll review some fundamental principles that are typically used in analyzing problems in hydraulics. That includes the equation of continuity, energy, and momentum equations. And then we'll spend some time on full pipe hydraulics, and then I'll wrap it up with open channel flow hydraulics, in particular two conditions called critical flow and uniform flow and how to compute those depths. There are some problems in the appendix that I've included. I will not include in our present session. Particularly loop network analysis and things like that. So you might want to, at your own free time, review those contents there. First, let's look at some units. Most of the time I've seen in the past, based on over the years I've taught this subject, a lot of times you'll make mistakes or students make mistakes in terms of units, using inconsistent units, what I call inconsistent units. So what I've taken is taken the liberty of listing both in the US system and the SI system of units some variables, so what we call fundamental and derived units. For example, mass, length, and time we know are fundamental in US units, in SI units, but force is the fundamental unit instead of mass in the US units. Some of the units that you'll see, at least in terms of hydraulics, is make sure that the units that you use are consistent. For example, unit of force is pound force. Unit of mass is a slug. In SI units, it's a kilogram, meter, and so on. Unit of force, for example, is Newton. It's pound force of course, in US units. The other thing we'll talk about quite a bit in this session is what we call the pressure head. And that is basically what we call P. And that is in terms of specified as a foot or a head. So it's in feet or in meters. We will also talk about pressure, of course, in the traditional units of PSI, but keep in mind PSI is not a consistent unit. Pounds per square foot is. And so is Newton per meter squared, or what we call Pascal in the SI system of units. We'll also come across power units, which is work done or rate of work done, which is pound-foot per second, or Newton-meter per second in the case of SI. So notice I'm using essentially consistent units to derive the units for the power or energy. Same thing with dynamic viscosity and kinetic viscosity. If you ever use these quantities or compute them, make sure you stay with consistent units and you will not make a mistake. Same thing with acceleration. It's all in feet and seconds and so on. Okay, so the bottom line is whatever formulas we use in the field of hydraulics, it's better to stay with consistent units unless you're using some kind of an empirical equation which calls for different types of units to be used in the equation. I'm also going to show you a slide here comparing two systems here. One is what we call pipe flow. And here we primarily will focus on pressurized pipe systems initially. That's what we refer to as pipe flow. But keep in mind that in urban stormwater systems, for example, we do use also circular pipes that flow like open channels. So what I've shown here is an illustration of the difference between them. Typically, in the case of a pipe, we measure everything with the center line of the pipe, with respect to the center line of the pipe, while as in open channel systems, we measure with respect to the bottom of the channel. For example, the flow depth, in the case of an open channel, represents P or gamma, or the pressure head, in terms of pipe flow situation. Keep in mind the illustration on the left side shows you a pipe under pressure. So if you stick a pitot tube or a piezometer, the water will rise to what we call the pressure head or hydraulic gradient line. And I'll define these later on in my discussion. But right now, the important thing for you to focus on is there are three terms here shown in these illustrations. One is Z1, which is the elevation head, we call it, or the height of the center line of the pipe from a datum, fixed datum. In the case of an open channel, that same Z represents the height to the bottom of the channel. And then, of course, as I said, in the case of a pipe, we may represent instead of the flow depth, we represent what is called the pressure head. That Y1 in the graphics on the left-hand side should, by the way, be P over gamma or P1 over gamma. And then we have the velocity head, which is V1 squared over 2G. That represents the kinetic energy component of the energy. In the case of open channel, you have also got V1 squared over 2G, where V1 is the average velocity. Of course, as I said, the pressure is replaced with the flow depth, which represents the pressure head in the case of an open channel system. So we'll discuss both just to cover both aspects of hydraulics. First, we'll talk about full pipe flow. In this case, the most widely used cross-section is a circular cross-section. Most widely used, you'll encounter full pipe flow conditions mainly in water supply systems and, of course, in urban storm sewer systems when they get pressurized. If they're not pressurized, urban storm sewer systems behave like open channel systems. Typical cross-section in open channel systems we come across are trapezoidal, and a special case of that trapezoidal is a rectangular section with vertical sides. There are also triangular sections. These are primarily used for small gutters, etc. So the main sections we'll talk about is trapezoidal and rectangular. Here's a graphics of a cross section, a typical cross section in open channel systems. In this case, a trapezoidal section. Some of the important hydraulic variables that you need to get familiar with in the case of an open channel cross section is, of course, the bottom width B, the flow area A, the flow depth, and the side slope is specified as Z horizontal to 1 vertical. And of course, there are a couple of others based on these parameters. What we call the wetted perimeter, which is basically shown as a dashed red line here, is the length of the bottom of the channel that's wetted by the fluid. In this case, the dashed red line that I've shown here is the wetted perimeter, P. The hydraulic radius is the ratio of A over P. Keep in mind, hydraulic radius does not really have a physical meaning other than the ratio of A over P in open channel systems. While as in a full pipe flow, I'll show you down the line, it does have a physical meaning. It turns out to be 1/4 the pipe diameter. The hydraulic depth, A, which is sometimes used occasionally, particularly in the definition of what we call fluid number, it's equal to A over T. That's the cross-sectional area divided by the top width. There are some special cases I've shown in this insert you might want to look at. For example, for the rectangular cross-section, the area is BY or B plus 2Y. That's the bottom width plus 2 times the depth. Remember, the side slopes are vertical. And the hydraulic radius is A over P, so its cross-sectional area is BY divided by the wetted perimeter will be B plus 2Y, which is shown right here. And therefore, the hydraulic depth is A over T. Now remember, for the rectangular cross-section, the top width, which is this part right here, is equal to the bottom width, since the sides are vertical. There's also a thing called a wide rectangle channel you might want to watch out for in problems. When they use this terminology, what they're getting at is the bottom width is approximately greater than or equal to 20 times the flow depth. What this does to the calculation is, or computation is, it makes the hydraulic radius very, very close to the vertical flow depth y. So R is equal to y for a rectangular channel, wide rectangular channel, and that makes a lot of computations fairly simple. It also gives a physical interpretation of the meaning of hydraulic radius in the case of an open channel system. Otherwise, it's always defined as the ratio of flow area to the wetted perimeter. Now, by the way, I want to also emphasize one more thing here, and that is in open channel systems, the flow area A, which is shown right here, is a function of the flow depth. That means as the flow depth changes, the flow area changes, the cross-sectional area changes. That is not the case with a full pipe flow. In a full pipe flow, the cross-sectional area is fixed, and therefore that makes computationally a lot easier to deal with a full pressurized circular pipe than to deal with an open channel system. Okay, and that's why we have two different types of hydraulic situations with these two systems. I've taken the liberty of providing you a table that you can use to compute cross sections. Remember, in open channel systems, the flow area and the wetted perimeter, all these are functions of flow depth. So it's good to have a table like this that you can use, formulas that you can use to compute the various hydraulic elements, I call it, of channel cross sections. I have shown this for a rectangular section here, trapezoidal, a triangular like a gutter type of thing, and also for a circular conduit flowing partially full, which I remember I said it's basically like an open channel system. It's a function of, in this case, the formulas involve an angle called theta, a sector angle, which is shown in this graphics here. Most engineers tend to use a nomograph, which I'll show you in a minute. But if you don't have the nomograph or you don't want to use it, you can go ahead and use these formulas. Just keep in mind that this theta is measured in radians, not in degrees. Okay, so for example, the cross-sectional area for a given flow depth is in terms of theta, which is this angle right here, which is a function of the flow depth y. So as the flow depth y changes, the angle theta will also change. Obviously, theta will go from basically 180 degrees for half the depth. If it's zero, of course, theta will be zero, the flow depth. And then, of course, the full depth, theta will be 360 degrees. So that's the general range of theta. You could use that to calculate the cross-sectional area, etc. What this table does not give you is an equation for the flow depth y, which you can easily derive from trigonometry, from geometry. Now, if not, I would suggest you use this nomograph. In this case, this is a very good thing to take with you. It allows you to calculate the cross-sectional area and all these so-called hydraulic elements for a circular conduit flowing partially full. And through an example, I'll illustrate to you, or I've set up an example for you. But in general, what you need to do is, for a given depth, for example, if the flow depth is 75% of the pipe diameter, that is the Y over D naught ratio, is equal to 0.75, then you can go across this graph and take any of these curves. For example, you can select the curve that's labeled A over A naught, and then get the ratio of A over A naught by swinging up here and reading that ratio, approximately in this case 0.82. And A naught, by the way, is the cross-sectional area of a full pipe flow condition, which is pi d naught squared over 4. Those are all shown in the insert here at the bottom of this nomograph. Same thing with hydraulic radius. If you want the hydraulic radius, instead of reading the curve A over A naught, you go right across and read the curve labeled as R over R naught. So let's look at a small example to illustrate this. Uh, First, let me show you what you might want to work with initially is a trapezoidal section. I've set up a small problem for you. For example, let's do the flow area here. You can send the answer through a chat box. In this case, I've given you a trapezoidal channel with side slope of 2, and the bottom width is 15 feet. And for a flow depth of 5, I want you to calculate all these hydraulic elements. But right now in this present session, let's try to calculate the area. You might want to go back to the table the slide where I had the formulas for you, and those were given in this slide right here. So use this equation for flow area, which is B plus ZY in parentheses times the flow depth Y. Use that to calculate the area and just go ahead and send me the answer. Somebody's already worked it out. There's another question from another gentleman. He says theta is in radians, yes, for the circular conduit if you're going to use the formula. Most of you are coming out with an answer for the flow area correctly, and that is C. Good. All right, you can do the wetted perimeter. That's basically as I said, it's a length. It's not an area. It's a length along the bottom of the channel that's wetted by the fluid. The formula for that also is given in that table I just shared with you. And the hydraulic radius, of course, is A over P ratio. So please work on this. Just get comfortable with it, how to calculate these elements for different flow depths. Here's a circular culvert. This is where I'm going to use the nomograph now. I'll show you, in this case, again, it's an open channel system because the flow depth, in this case, one I'm giving you, is equal to 3 feet. The pipe diameter is 4 feet. So you know that it's flowing partially. And in order to say, for example, to calculate the area associated with a flow depth of 3 feet, we'll go ahead and use the nomograph. To get there, so this is number one here. Here are various alternatives. So first thing you calculate is the ratio of y over d naught, which is the pipe full pipe diameter, which is in this case 4 feet. This ratio in my example happens to be 0.75. So if you go back to the nomograph that we had, it turns out to be the same point that I was showing you earlier. So we've already gone through that process, go across for the ratio of 0.75 and read where it intersects this curve A over A naught labeled. And that turns out to be about point, I would say 82, 81. And so it's a little bit approximate. You can make it more accurate if you want. But the flow area in that case will be the ratio of basically what we got is 0.82 of the full pipe diameter. And the full pipe diameter, full pipe area is pi d naught squared over 4, which in this case is 12.6 feet squared. So if you take about 80% of that, you know where what the answer will be. So if you can do that briefly, you can verify it for yourself. Somebody's already done that. Very good. So yes, it's anybody else? Just multiply 0.82 with the full pipe flow area, and you get the answer. Answer is B, yes. So let's move on to now the next slide. I just included two small topics in here because I was told you might get some problems involving flow measurement in pipes. Typically, these are the devices we use called venturi meters, and another one is called the orifice meter. And typically what you need in order to calculate the discharge using these instruments is a rating curve. I call it a rating curve, but essentially what it is, an equation, a mathematical equation to calculate the flow rate in the venturi or in the pipe. What the venturi meter does is essentially constricts the flow and thereby increases the velocity at a point called the throat of the venturi. By doing so, it converts essentially the potential or pressure energy to kinetic energy. So therefore, there's a pressure drop observed in the process, and that pressure drop is typically measured by a manometer. In this case, that pressure head drop is given by this term in the parentheses here, R prime, ratio of two specific gravities minus 1. The two specific gravities, S0 and S1, or 1 is the specific gravity of the fluid in the inside the manometer, which in this case is labeled as S0, shown right there. Sorry, that one right there. And S1 is the specific gravity of the fluid going in the pipe itself, whatever it is, maybe water. So obviously you want to use a fluid that doesn't mix with water, so typically most people like to use is mercury, which has a specific gravity of 13.6. So therefore, I'll show you an example on how to use this equation, this rating equation. But there's a question of discharge. Most venturi meters are pretty efficient in terms of losses, so their CD value is about 0.95 to 0.99. Obviously, a CD of 1 is 100% efficient. That means there's no losses whatsoever. Watch out for this A2 here. A2 is the area of the throat, what we call the throat of the venturi, and that's based on the size of the pipe at that point. Also, there's a ratio of two diameters here, D2 over D1. D2 is the diameter at the throat, and D1 is the pipe diameter at section 1 here. So anyway, this is a device that's used for measuring Q. We have another one called the orifice meter. The fundamental difference between these two is in an orifice meter you have an opening, and that again basically constricts the flow, thereby increasing the velocity. So it does a kind of similar thing that Venturi does, and of course the CD of course is lower than the case of Venturi because there's more head loss associated with a device like this. The equation looks the same, the rating equation. Once again, you can calculate Q given the information on the right-hand side. To give you an example, I did one for Venturi meter. You can kind of set it up for an orifice meter the same way. Here's the flow of water. Specific gravity is 1. It goes through a 24-inch pipe, that's D1, using a Venturi meter with a 6-inch throat, that means the D2 is 6 inches. Now remember, since we're taking the ratio of these two diameters, we don't have to convert to consistent unit of feet. The gauge difference in the manometer is 11.8 inches. Again, it's given in inches, so be careful because the consistent unit, as I pointed out to you earlier, is feet, not inches. So it's 11.8 inches. That's your R prime in the equation. Assume a coefficient of discharge of 0.95. And here we go substituting all these given quantities like CD is 0.95. And then, of course, A2, you have to calculate that, the area of the throat, which is 6 inches in pipe size, but it has to be in square feet. And I've calculated that for you right here, pi d squared over 4. Notice I'm converting the 6-inch pipe size into feet to make it consistent. And then, of course, the pressure drop, that term that I told you in the equation, R prime times S naught over S1 minus 1 is really what I call in hydraulics a pressure drop delta H. And that will be, if you use consistent units, come out in feet. So in this case, 11.8 inches divided by 12. Yes, are you all not able to hear or something? Let me see. Could you please slow down? Yes, I will do that. Somebody said about CD, will it be given in the problem? Yes, the CD will be given in the problem. If not, as I said, you might have to assume it. For a venturi meter, it's about 0.95, and for an orifice meter, typically around zero point 0.6. Now, here's the equation that I was looking at as an example. In this case, the CD, the coefficient of discharge, is given as 0.95, and therefore I'm going to use that essentially in the equation here. Also note that the pressure drop that we calculated is about 12.39 feet of water, and therefore is substituted in this equation to calculate Q. So the final product is Q, which is CD times that pressure drop, and of course multiplied by this quantity called, or divided by 1 minus d2 over d1 to the power of 4. So you all can do these calculations. I've just shown it to you in this example. The final flow rate through the pipe is 5.27 CFS. So the primary purpose of venturi meters is to measure the discharge. And I will try to go as slow as I can. If I'm going a little fast, please let me know. The next thing we'll talk about is the flow measurement in open channel systems. Just like venturi meters and orifice meters in pipes, we have similar devices for open channel flow systems. It's called a partial flume. And all I'm going to show you is the rating equation here for a partial flume. The idea in this case is similar to the venturi meter. If you look at the plan view from the top, notice what they're doing to the flow. The flow comes into the channel system and is constricted. So when you constrict the flow velocity increases, just like in a pipe. And when it does that, the flow depth is going to change or drop, and that's what we need to measure is the drop in water surface, as opposed to, say, the pressure drop that we saw in a venturi meter. So that head drop or head difference is what we usually capitalize on determining the Q. So the Q equation is given here. Just be a little careful in using this equation. We have 4W, that's the width of the throat. Uh, and then somebody asked me, where do you place the flume? Anywhere in the channel system where you want to measure the flow. For example, in the case of wastewater, that's where it's usually used is in water treatment plants. They put these partial flumes where the water comes in for treatment, and at that point where they want to measure the total discharge coming in, and this is essentially where they can place it. Somebody asked me, are these images a plan and profile view? Well, this is a plan view from the top, and this is the profile view, okay, of the same thing. That explain your question? Okay, somebody asked me about a parentheses. Yes, I will explain that if to elaborate that. For example, this equation is 4 times W times h to the power 1.522, and that whole thing is raised to the power W raised to the power 0.026. I know this is a little messy, so what I suggest is in using this equation, first calculate W to the power of 0.026, and then multiply by 1.522, and then that becomes the new exponent for h. Is that clear? So if you want to put parentheses, that's fine. I don't see the need for it. There's an example, I think, on the next slide, but I show you how to use it. But make sure the units are consistent. And here's the equation, and I've set up a small example for you. As I said before, in this case, you have a partial flume with a throat width of 5 feet. That's one of the variables. And it has a free-flowing upper head of 1.5 feet. And that's all you need in order to calculate the Q here. So notice here what I've done, W to the power of 0.026, so I take 5 to the power of 0.026 first, and then whatever I get, I multiply by 1.522, and then raise that new exponent to the power 1.5, and finally I calculate the Q. It comes out in CFS, the answer. That's a consistent unit. Uh, Typically in wastewater systems, we use a unit called MGD, million gallons per day. For those who do not know the conversion factor, I suggest you take one with you. I can tell you right now what it is. 1 MGD is 1.55 CFS. So if you want to make a note of it, that's fine. Million gallons per day is a preferred unit of measurement in water supply and wastewater systems. Well, now the crux of our discussion this afternoon will be fluid dynamics, some of the principles that we use in solving problems, both in pipe systems and open channel systems. Somebody is asking me another question here. Can you show us what H represents in the evaluation elevation of plan view? Sure, I will do that before I start this. H is the, okay, it's given right here in the label. It's the height of the water surface before it gets into that slope area right here where the water starts accelerating. So that H reflects the effects of this throat on the whole flow situation, okay? And that's what H is. I hope that answers your question. All right, moving on. Let's talk about some basic principles of fluid mechanics that we use quite often. There are three of them. I'll review all three, and I'll show you how to use them, both in pipe hydraulics as well as in open channel systems. The first one is called the law of conservation of mass. Although we call it law of conservation of mass, in the case of water, we know it's incompressible. Really, this takes the form of law of conservation of volumetric flow, or we call equation of continuity. And that's because the density is constant, and therefore it's not a factor in the equation. So for steady, incompressible fluid, which is the density being constant like water, both in a pipe or in an open channel system, this law of conservation of mass is stated as Q, the flow rate, is equal to V1A1 equals to V2A2, where V1 is the average velocity at a section, where the cross-sectional flow area is A1, and the same thing is on the right-hand side, V2A2, it's at another cross-section. So most of you are familiar with this. It's called equation of continuity. And by the way, in many, many problems on the exam, they may not give you or ask you to use this explicitly. You have to know that it is always valid, at least for steady flow. Most of the time, that's what you will see on the exam, is a steady state situation. So it's not a function of time, and therefore flow coming in must always be flow going out. Keep in mind, I will not spend too much time about this concept of average velocity, and that's what we use in most of our problems. It's like a uniform velocity across the entire cross section. That's not a major problem in a pipe situation where the flow is flowing across the entire pipe. It might be problematic in an open channel system. So we do put a correction factor for utilizing the so-called average velocity. I'll explain that when we get to those specific situations. Q is the volumetric flow rate, or discharge we call it in CFS. A is the fluid area. In the case of a cross section, in the case of pipe flow, full pipe flow, A is constant. It's equal to the pi d naught squared over 4. I've set up a small example here. In this case, I have a full pipe flow situation. At section 1, the velocity is 3 feet per second, and the diameter of the pipe is 2 feet. And of course, at section 2, what I want to calculate is the velocity and discharge in this pipe. Of course, to calculate the velocity at section 2 here, we have to know Q, the discharge. So the first thing we'll do here is use the upstream conditions that are given to calculate the flow rate, which in this case is V1, A1. V1 is 3 feet per second, and the area of cross-section is pi d naught squared over 4. Please be very careful in this computation because many problems, they give you the diameter in inches. They never give it to you in feet. For example, in this problem, the diameter at D1 typically would be 24-inch pipe. So you have to convert that to feet before you do this calculation, because feet is the consistent unit. And in this case, the Q is 9.42 CFS. And using that discharge, I can then calculate the velocity at section 2. It's obvious. In this case, the pipe size is bigger at section 2. From 2 feet in diameter, it's gone to 3 feet in diameter. So we already know what to expect. The velocity is going to go down, which is basically what has happened. V2 is 1.33 feet per second as opposed to 3 feet per second at section 1. Once again, just to check, my Q is constant. I just recalculate Q2, which is V2 times A2. And notice that in this case, it's also equal to 9.42 CFS. So that's the equation of continuity in pipe flow situation. I have formulated a problem for you to go work it at home for an open channel system. Let me briefly tell you what the differences will be between the two systems. If you keep in mind that the flow depth is what's normally given in the case of an open channel systems, it takes the place of pressure head in a full pipe flow situation. Also, we have the velocity, average velocity, just like we had in the pipe system. We have it also in the open channel system, except that the average velocity is a little more difficult to define in the case of an open channel system. But for this part of the exam that you're taking, I would just leave it at that. It's typically will be given to you, the average velocity. If not, keep in mind the average velocity can always be calculated using the flow rate Q. So Q over the cross-sectional area will also give you the velocity from continuity equation. So in this case, at section 1, I have a velocity of 4 meters per second, a depth of 4 meters. Now remember, V1 times A1 should give you really the Q, but in this case, what I've given you is a rectangular channel with a flow depth of 4 meters, and the width of the rectangular channel is also given here. It's an 8 meters wide. So the flow area for a 4 meter depth would be 4 times. That's the depth times the width, which in this case 32 square meters. So therefore you can take that area, multiply by velocity to get the total discharge. What I'm going to do is introduce a new variable called discharge per unit width, just to illustrate to you that concept. It's normally for a rectangular channel, it's equal to the discharge per unit width. That's what that it translates into. So it's capital Q over B. Capital Q, by the way, is the symbol we use for discharge or flow rate. Now, you all can go and do this first part. Let's get an answer for that. For this particular problem, tell me what the discharge per unit width is in this channel. That should be fairly quick and easy to calculate. Somebody already came out with the answer, 16. Yes, so that is the correct answer. That's because, how did we get that? We got the discharge Q divided by the unit width. 8 meters is the width. Notice what happens here. When I divide by the width, essentially the small q can be obtained by taking the flow depth times the velocity directly in a rectangular channel. So y1 is, in this case, 4 meters. v1 is 4 meters, so 4 times 4 is 16. Okay. So the units of small q are meter cube per second per meter, or CFS per foot per foot. Okay. It's a commonly used discharge variable in open channel systems. The most important equation, of course, the second equation that we'll review. This is called the Bernoulli equation, we often refer to as the energy equation. I want to emphasize this because in many, many problems dealing with pipe systems or open channel systems, typically you see the application of this equation. All it is basically says that total energy at any cross section or at any section of the pipe or the open channel is equal to sum of 3 terms. The first term is called P over gamma. We often refer to as pressure head. Now notice the word I'm using, head, and I'll explain that in a minute what that means. The second term is a potential energy term, or basically this is the energy the fluid possesses by virtue of its elevation above a datum. And then of course V squared over 2G is what we call the kinetic energy or velocity head. So basically the first 2 terms represents like potential energy and pressure energy together. And finally, Third term represents the kinetic energy term. And of course, if there are any losses, we will have to abstract them or recognize that, minus head loss. And if you add any head to the fluid, like a pump or something, we always do plus HP. So the next two, those two terms, HL and HP, represent the head loss or slash head gain in a fluid. Whatever it is, the whole thing must be a constant at that cross section and must not change from section to section. Now, one of the things I would like to say is the word head. Head is measured in feet or meters. It represents essentially the energy at any cross section in terms of feet or meters. The sum of the first two terms by the pure gamma plus Z we often refer to as the hydraulic head. It's the pressure head plus the potential energy or elevation head summed together. That takes a lot of importance in water supply systems, as we'll see later on in one of the examples, primarily because, as I will illustrate to you in a minute, the sum of these first two terms is more dominant than the third term, the kinetic energy term. Usually you'll find in many, many problems, V squared over 2G will be quite small. Anyway, these are all expressed, as I said, in feet or meters. And let's look at the next slide. I've got a small example also, not this slide, but the one following this. For an open channel system, I can define the same thing as I did for the pipe system. The total head at any point, or the total energy if you want to call it, is Y. Instead of P or gamma, I substitute the flow depth, Y. By the way, this is the vertical flow depth. I won't get into the debate about whether that is accurate enough to use that. We're just going to use it for small slope channels. It's quite reasonable to assume the vertical flow depth represents the hydrostatic pressure at the bottom. Finally, Z, that's the elevation to the channel bottom. Remember that. And of course, V squared over 2G kinetic energy. Now, I do throw in a term here, a coefficient called alpha, which we often refer to as a kinetic energy correction factor. And that typical range of that coefficient, by the way, is between 1 to 1.3. If they don't give it to you, just assume 1. Okay? Why is it there? Well, I won't get into the details of it in this discussion, but essentially, the moment you represented using average velocity in a cross-section in a channel, I always told you that the actual velocity cannot be the average velocity because of the fact that the velocity at the channel bottom, for example, must be 0. And as you go to the center of the channel, the velocity increases, reaches the maximum value. So it's a non-uniform distribution. But the fact is you're substituting or assuming a uniform velocity distribution across the entire cross-section. And the price you're going to pay there is, of course, that's not an arbitrary assumption, by the way. It assumes you do that assumption with the fact that the same flow volume is going through at both the cross-sections, both the velocity distributions, the actual and the average. But the kinetic energy transport is not the same because it's the sum of V squared over 2G. So in order to make the kinetic energy transported equal in both velocity distributions, we have to correct it through a coefficient called alpha. Okay, and for the sake of discussion here, most of the time we neglect it, so it'll be 1. So don't worry about it too much. But those are the three terms in the open channel system. Now, all these head units or head terms in the Bernoulli equation, I told you represent energy or power, and to really show that or to convert them into actual energy units, you have to use this equation. So try to memorize this or take it with you. Very often, we always like to find out what that head means in the Bernoulli equation. Remember, we call it the energy equation. So this head H can be converted into work done or power by multiplying by Q, the flow rate, and the specific weight of the fluid gamma. Now, for those who are not familiar or forgotten specific weight, it's basically gamma is the density of a fluid times G, rho times G. So in the case of US units, gamma of water is 62.4 pounds per feet cubed. In SI units, gamma is 9806 newtons per meter cubed. And how I got that? Rho times G. You have to know one, at least the density of water to get that value. For example, density of water in US units is 1.96 slugs, 1.93 slugs per feet cubed. So to multiply that with G, which is 32.2, you'll get 62.4, okay, approximately. The gamma, of course, consistent unit in US unit is CFS. So keep the units, respect it. I've given you here all the units. In SI system, of course, the power comes out in Newton meter per second, which is called joules per second or watts, okay? And of course, Q will be in meter cube per second, and the head will be measured in meters. Gamma, in my example here, let's go through a small example. Let's say, for example, you have a pressure head P over gamma in the Bernoulli equation of 50 meters, which, by the way, turns out to be 490 kilopascals of pressure. That's P over gamma. And Q is, in this case, zero point 0.6 meter cube per second. Then the water power, the amount of energy that that particular fluid possesses, is obtained by using this formula gamma, Q, and H. So in this case, gamma is 9806, and Q is zero point 0.6, and therefore, you multiply all these three quantities, you end up with 294,180 Newton meter per second or joules per second. Remember, that's also called a watt, a W, that's the unit of power in SI system of units. As we know, kilowatt hour is quite a popular unit uh, in many energy applications. And that's 1 hour of usage, by the way, when they say kilowatt hour. But kilowatt is 1,000 watts, is the unit of power in the SI system. We do not have an abbreviated acronym in the US units. We just call it pound-foot per second. There's also a unit called horsepower. Please try to get familiar with that. It's just a unit that's used to scale energy or power. For example, in the SI system, 1 horsepower represents 776 Newton meter per second. So if you have energy in Newton meter per second, it's usually a large number. Convert that to horsepower by dividing it with 776. The one in the US unit is 550. Somebody has a question here. It says, what is 9806? What is the 9806? Well, that's gamma, specific weight of water. Remember I said in this equation you have gamma QH. Gamma is the specific weight of water, which is density times G, acceleration due to gravity. Okay? And for SI units, gamma is equal to, right, density of water, which is 1,000 kilograms per meter cubed, times G, which is 9.806. So if you multiply the two, you'll get 9806. Okay, that's the gamma of water. You might want to memorize that if you don't know how to calculate it from density. The same thing in US units was 62.4, if you remember, pounds per feet cubed. Okay, so you're probably more familiar with the US unit, but not the one in SI units. So this is gamma right here. Does that answer your question? I hope it does. Okay, all right, moving on. Uh, Here's another example I've set up for you to get yourself familiar with each of the units, each of the quantities in the Bernoulli equation. Let's kind of review these because this is very important for some of the problems I'm going to do down the line. For example, here the flow is in a 24-inch pipe of 20 CFS. The pressure at a point is 60 psi. Typically, that's how we measure pressure. It's also what we call a gauge pressure, that is related to the atmospheric pressure. We do not use absolute pressures in fluid mechanics. Gauge pressure is basically the relative pressure relative to the atmospheric pressure. So it's absolute minus the atmospheric. So anyway, 60 psi is the pressure above the atmospheric pressure. It's positive. It's pounds per square inch. But the consistent unit of pressure is not psi. It's PSF, pounds per square foot. So we have to convert that right away to PSF before you do anything with it. Typically, to do that conversion, we multiply by 144, as I'll show you in this example here. What I'm going to do here is to show you, bring all these head units into one common unit called feet. So a pressure head, P over gamma, is 60 psi of pressure multiplied by 144 converts that to PSF. You should do this and divide by the gamma of water again, which is 62.4. This example is in US units. In SI units, you'll obviously have Pascal is the unit of pressure. It'll be in newtons per meter squared. So remember, you do the same calculation. You don't have to do this 144 thing because it's already given in pascals, consistent units. But the gamma of water is 9806. Remember the 9806 we saw in the previous example? That's what you use right here. That's a specific weight of water. Anyway, in the case of US units, the answer comes out in feet. So this pressure of 60 psi represents 138 feet of water column, of a water column. Okay, that's the head. So if you were to take a 138 foot of water column, measure the weight of that column at the bottom of that column, you'll end up with a pressure basically in pounds per square feet or pounds per square inch, 60 psi. That's what that pressure represents. Essentially, it's the weight of the water. Then Z, of course, you don't have to convert. That's already in feet. It's in elevation. The velocity is the other one. In order to convert that, we do V squared over 2G. That's the kinetic energy head. Notice what happens in this. First of all, use consistent units, please. That's very, very important. In this case, velocity must be in feet per second. And V squared over 2G is shown right here. It's 6.4 squared divided by 2 times 32.2, which is 2 times G, gives you 0.64. Now, if you look at these numbers, remember the Bernoulli equation, I mentioned 3 terms. P over gamma plus Z plus V squared over 2G. These 3 terms together represent the total energy of that fluid at this particular cross section. If you look at these 3 terms, the most dominant one, of course, is elevation. Of course, that's related to a datum. But if you look at these 2 terms, P over gamma and Z, they definitely are a lot larger in magnitude than the velocity head. So in many, many pipe problems, we tend to, if we neglect this velocity head, you'll be fine. So keep that in mind because in some situations, some problems, the velocity may not be given, but you have to pretty much assume that the velocity head is going to be small or negligible. So you can go ahead and apply the Bernoulli equation. In pipe problems or water supply systems, this is very, very true. Most water supply engineers will track the changes in P or gamma plus Z combined. That's called by the way, that's called the hydraulic head or the piezometric head. Okay, so keep that in mind. They track that because the velocity head to them is fairly small. The changes in that. So in this case, the total head, if you add all 3, is 639.14 feet. And then I took the liberty of converting that to energy or power. In this case, gamma QH. In order to calculate power, you have to be given the Q, the flow rate. It is a function of that. The more the flow rate, the more the power. So the same amount of head, as in this example, if the flow rate was doubled, then the power will also be doubled. That should tell you something because in turbines and when you run turbines where you generate power, it's a function of both the amount of head that's available to you as well as the flow rate that is going through the system. Gamma, of course, you can't do much with that other than change the fluid. But right now with water, it's 62.4. So here's the calculation. Unit of this computation will come out in what? Pound foot per second. Okay. As I said, horsepower is a preferred unit. If you divide by 550, it scales to 450. Okay. So this example shows you all these various quantities. Also, I want to go with this because sometimes in some questions they ask you the definition of or the quantification of what we call the hydraulic gradient line or the EGL, energy gradient line. They call them AGL or EGL. All it is at any cross-section of the pipe, at any point in the system, they want you to plot the sum of these 2 terms. P or gamma plus Z term is called the hydraulic gradient line at that point, or AGL at that point. If you sum the kinetic energy also into it, then the sum of all 3 is called the energy grade line, or EGL. So all these lines represent is what the total energy is or what the total hydraulic grade is at a particular point in the fluid, okay? So keep that in mind. Of course, for an open channel system, you'll have to substitute P or gamma and substitute Y, the flow depth for that. So therefore, for an open channel system, the hydraulic gradient line is y plus z. Now, if you think about it, what is y plus z? It's basically the flow depth, vertical flow depth, plus the elevation of the channel bottom above a datum. So that's essentially what we call the stage or the water surface of the channel system. So it takes you to the water surface of the channel system. So therefore, the hydraulic gradient line in an open channel is the water surface. Okay, so if you take a boat and ride along a river system, you're riding along the AGL. You can't do that in a pipe system because the pipe system is under pressure. I've set up a small example to show you how Bernoulli equation is used. Let's go through this small example, and typical problems will be like this, where they'll ask you to analyze, determine some unknown quantity. Now remember, if you use the Bernoulli equation, you can only have one unknown, because since you have one equation. So in this case, a pump delivers an oil. Now keep in mind, it's an oil, it's not water. The Q is 5.62 CFS, specific gravity is 0.762. From a reservoir A to reservoir D, the loss of energy, in this case the head loss, I'm going to give it to you. Next time I'll show you how to calculate them. And then from B to C is also given. So I'll kind of go through this a little bit fast because we've got to cover a lot of material here. So essentially what I'm going to do is, to apply the Bernoulli equation, I select 2 points. The most logical points to pick in this case would be point A and point D, because both at these 2 points, the water surface in the reservoir is what I call a free surface. The gauge pressure there is 0. And also the velocity head is negligible in reservoirs. So one could therefore write the Bernoulli equation between A and B and be able to solve for whatever unknown. In this case, what I would like to know is the head delivered by the pump to the water system and its horsepower. So a pump is delivering water from A to B, A to D, and we're trying to find out what that head delivered by the pump is. So what we do is we simply write the Bernoulli equation between point A and point D here. And here it is. PA over gamma plus VA squared over 2G plus ZA represents the total energy at point A. Plus any head delivered to the system. Doesn't matter where the pump is. This simply is an energy budget equation. So plus head delivered by the pump minus any head loss. Now remember, you're going from point A to point D. And therefore on the right hand side must be the total energy at D. PD over gamma plus VD squared over 2G plus ZD. I suggest you write the whole equation, and then you can always neglect or equate to 0 whatever quantities that need to be. For example, PA over gamma is 0 because it's a free surface at point A. The velocity head in a reservoir typically is negligible. It's very small. ZA is 50 in this case. The datum, height above the datum is given. Remember, point A is at the water surface, right? You're shown by the triangle there. The head delivered by the pump is unknown, so I'm going to call it H pump. Of course, the two losses between section A and section D is 8.25 plus, this is given the head loss, 21.75. So add them together, and that's due to friction, minor loss of whatever you may have. And on the right-hand side, PD over gamma is again 0, velocity is negligible, and the height of point D is 200 feet above the datum. So if you put it all together, the head delivered by the pump is equal to 180 feet. Why is it 180? Well, it's equal to essentially the elevation difference between A and D, which is 200 minus 50, which is 150, plus any head loss that it has to overcome. In this case, that head loss is 30 feet. So 150 plus 30 is 180. So it makes sense that the pump has to deliver 150 feet of head in order to take the oil or take this fluid water from one end to the other. In order to convert that to horsepower, by the way, this is an oil. Here's the computation. Gamma of oil is specific gravity times 62.4 times Q times H. There's your power that is needed in order to make this fluid delivered from A to B. In terms of horsepower, it's 87.46. Now, they'll always throw in an efficiency term sometimes. They'll say the pump is 80% efficient. What should be the horsepower of the pump? Well, the way I look at efficiency is, if you keep in mind that this is the amount of energy that's delivered to the fluid, if the pump is only 80% efficient, it has to have 20% more horsepower in order to deliver, correct, to overcome the losses within the pump. So you divide by zero point 0.8 to get the true horsepower of the pump in this problem. Okay. So efficiency, I don't want to give you a formula. It's best to handle it logically by remembering what each of these terms represents. Okay, moving on. And here I've taken the liberty to plot the EGL and AGL we just discussed for the same system. Please review this on your own time. And I've set up a nice problem for you to apply. I strongly recommend you work through this problem because I've had previous participants run into some problems. I'll be happy to answer any questions. You can email me, particularly this number 3, because this asks for basically the pressure intake at point B. So that kind of forces you to write the Bernoulli equation between A and B. Remember, I was trying to avoid that because the pressure at B, it's an internal point, and there is pressure there, PB or gamma, and that's an unknown. So you'll have to use the Bernoulli equation between A and B. Of course, the head loss is given, remember. I already gave you from A to B is 8.25 feet. So given that, go ahead and write the Bernoulli equation and solve for the pressure at point B. By the way, there's a concept of, in pumps, when it comes to pumps, there's a process called cavitation of pumps. That will not happen in this system because the gauge pressure will be positive here. Usually that's an issue or concern if that pressure there drops below the vapor pressure of water. I won't get into that. That's maybe an advanced topic for the morning session. But if you want to know about it, you can always read a little bit on pumps or pump hydraulics. I've also set up another example for application of the Bernoulli equation open channel systems. Let's, for example, the total energy, let's do this one here. Its velocity is given at that section V1. The depth is Y1. By the way, this is a rectangular channel. It's 8 meters wide. And the elevation head is Z1 is 100. So can you go ahead and tell me what the total energy H1 is at section 1? Now remember in the Bernoulli equation we have 3 terms. Instead of P over gamma, you'll be substituting Y, the flow depth. Somebody asked me, do you have solutions? Well, I will give you on a case-by-case basis. I don't have the solutions. I do have the answers, though, posted at the back of my presentation. I'll show you when we get there, the last slide. So I do have the answers for these problems, okay? I would like you to attempt them, and then if you run into a problem, I'll be happy to give you the solution. So it's always good to try them out first. Okay, the answer to this, somebody's already coming along with this. I don't see 100.81 on my answers here, one of my options. I don't know how this gentleman got 100.81. The ones are A, B, and C here, and D. Anybody come out with that answer? Remember, Z1 is 100. By definition is Y1 plus what? Z1. That's already 104. So you cannot have 100. And plus V squared over 2G, okay? So please, whoever that gentleman is, might want to work it again. The total energy for this particular cross section. The answer will be, give you a few minutes. Alpha is 1, by the way, so you don't have to worry about that. For those who forgot the equation, I'll go back one slide, maybe a couple of slides. This is the equation right here. The total energy in an open channel system. Okay, remember Y, the flow depth Z, and V squared over 2G. Alpha is 1 here. Okay, in any case, I cannot wait too long, so we'll proceed. I'm sure you can work this out at your leisurely. The answer, by the way, in this particular case will come out to be C. Okay. Let's move on to some pipe hydraulics now. We want to, one of the things they'll probably ask you in many, many problems is to compute 2 types of losses in pipes. One is called the friction loss, the other is minor loss. This sets the stage for analyzing pipe systems. Typically the total loss is the sum of the 2. Friction loss is basically occurs throughout the pipe. It's a function of basically the pipe itself and the fluid flow. Minor losses are usually due to fittings, such as valves and things like that. So I'll review both these losses, how to compute them. Before I do that, I'd like to emphasize one thing. I always found this type of approach very, very convenient, particularly in solving pipe problems. The head loss due to friction can be represented by this equation, kq to the power of x. K is a coefficient. I'll show you how to calculate in the next few slides, but it's a function of Q, the flow rate, and X is an exponent depending on which method you use to compute the friction loss. X, I'm going to discuss two methods here. One is the typical one that you probably already familiar with, called the Darcy's Weisbach equation. For that, X is 2. And then, of course, the one that's most widely used in water systems is called Hazen-Williams. For that, X is 1.85. So in either case, all units must be consistent. For example, head loss due to friction will be in feet, Q in CFS. Now K, I'll show you how to calculate. That's like I don't want to call it a friction coefficient because it's not. I'll just call it a head loss coefficient. And in this case, on the next two slides are the equations for K. It's very important that we understand this or take it with you. It's important you calculate it accurately. The first one is for Darcy's Weisbach equation. I will not emphasize that equation too much here, but nonetheless, you should know when you go to solve some problems how to use this equation. This is head loss is equal to kq to the power of x again, where x is 2.0, and here's the k value. F, as you all know, is the friction factor in the pipe, typically obtained from Stanton-Moody's diagram. It's a function of Reynolds number and the relative roughness of the pipe. And I'll show you that diagram in a minute, but that's how you obtain the friction factor F. Unfortunately, that friction factor F depends upon not only the relative roughness of the pipe, it also depends on the Reynolds number, which in turn depends on the velocity in the pipe. So, for many, many problems, when you try to solve them, you really do not have the true friction factor till you do a trial and error method. That's why I like to avoid it generally. Unless they force you to use it, I suggest use Hazen-Williams, where I'll show you we can assume their coefficient of friction to be constant. Here's the K for SI units. On the next slide is the Hazen-Williams, and I'll use that and I'll show you that in a minute. But here's the Stanton-Moody's diagram that we talked about. It's a friction factor F, Reynolds number, and of course the relative roughness. If you're using the Darcy's-Weisbach method, you've got to get familiar with this diagram. Most applications, you probably have to estimate the Reynolds number, and of course the relative roughness depends on the type of pipe you're using. Those two combined will give you a friction factor. For example, if the Reynolds number is 10 to the power 6, which is pretty turbulent flow region, and say the relative roughness is 0.002, you go across and read your friction factor on this axis. By the way, the relative roughness, epsilon over d is dimensionless, so it should be unitless also. So if epsilon is in inches, make sure the diameter is in inches. If epsilon is in feet, diameter must be in feet also. That's called I leave this to you for review. I want to spend more time with the second method, which I believe if they don't specify is the easier one to use, primarily because this Hazen roughness coefficient can be fixed or held constant with minor adjustments for the pipe flow velocity. Okay. Now, Hazen-Williams is the same type of equation in the same form, where K is equal to 4.73 L divided by C to the power 1.85 D to the power 4.865. Make sure you calculate this very, very carefully for each problem because I do not have a physical interpretation of K. Therefore, we do not know if we got it right or wrong. L is the length of the pipe in feet. C is the Hazen's roughness coefficient. I'll show you a table. You can get it from there. And D is the pipe diameter in feet. Not in inches, but in feet. The exponent, don't forget, is 1.85. In SI units, it's the same equation except it's 10.7 L. L is in meters, not in kilometers. C is, of course, the same roughness coefficient as before, and D is the pipe diameter. Now let me show you a table. First, before I show you a table for C, some notes on the Hausen-Williams coefficient C. First of all, you have to make a note. Next table, I'll give you the typical values, but the most important thing is the higher the C value, the smoother the pipe, unlike the friction factor F, the Darcy's. Remember, in Darcy's, the smaller the F, the larger the, more the friction. The higher the F value, the more the friction. So rougher the pipe. But in the case of Hausen C, it's just the opposite. A smooth pipe has a C value of 150, for example, a PVC pipe. An old pipe has a C value of about 60 or lower. So these are some things to know. Also, generally the method is valid for velocities in the range of 6 to 9 feet per second. Most water supply or pipe problems fall into this range. If not, they also recommend a small adjustment in the C value. A plus 5% increase in C is recommended if the velocity is obviously below 6 feet per second. Okay, so between 3 to 6 feet per second, for example, you increase the C by 5%. Why? Well, the smaller the velocity, the less the head loss due to friction, and that means you want to increase the C value to make it smoother. And on the other hand, if it's if the velocity is outside 9 feet per second, say 9 to 12, in that case, you basically decrease the C value in order to reflect that you'll have more head loss due to friction. Okay, so that small adjustment is needed in applying this method. But unlike the Darcy's-Weisbach equation, which is you don't have the trial and error to deal with in this situation. Here's the typical C values in this table. Again, a cast iron pipe, for example, right here, it's got a C of 130. A steel pipe has a C of 120. So you can consult this table from the description of the problem, select your C value. Minor losses. These are due to fittings and pipes normally, and most of those fittings, the head loss can be associated with those fittings can be expressed in this form. Km V squared over 2G, where V squared over 2G is the velocity head. Km is basically the minor loss coefficient. Now I can rearrange this also into the same form as we did for the friction loss, and that is in terms of Q, the discharge. Recognizing the fact that Q over A is velocity, and therefore manipulate that equation and finally into this form where K prime is now a function not only of Km, but also the cross-sectional area of the pipe, which is okay because most of the time that is true. It depends on the fitting, which pipe it's in. The size of that pipe is important also in the head loss situation. Here's the typical Km values. These are the minor loss coefficients. For example, a fully open globe valve is 10, an angle valve 5. You'll also have to sometimes deal with what we call entrance losses and exit losses. Those Km values are given at the bottom of the table. Okay. I've set up a small example for you to calculate particularly these K values, and then, of course, finally in step number 3, to calculate the head loss in this particular pipe situation. You got a 12-inch pipe, 1,500 foot long. Hausen C is 120. The flow rate is given as 5 CFS. So the first thing you will do in many, many problems is to calculate that loss coefficient I told you, K. In this case, it's 4.73 L over C to the power 1.85 D to the power 4.865. I suggest if you have, I think we might have a few minutes here, just go ahead and calculate this. I just want to make sure you get the right answer. So go ahead and try this, see what you come up with for this particular problem. Remember, there's no other way to verify this because it all depends upon these variables here, L, C, and D. So go ahead and substitute these in consistent units and see what you come up with. Give you a few minutes because then once you know the K, you can calculate the head loss, which is number 3 here. But let's do the K to make sure You know how to do it. Do I have any volunteers? All you have to do is substitute L, the length of the pipe, which is given, because C to the power, that exponent 1.85 can be a little tricky. 120 raised to the power 1.85, and the pipe diameter is given here, but make sure it's in feet. That's the only thing you have to do, make sure of. Any answers? No. I hope y'all can hear me. I don't know. Maybe y'all are a little bit tired of doing computations. I don't know what's. I hope y'all can all hear me clearly. So anyway, we'll move on because I've got some other stuff to show you here. So that's how you can. In this case, the K will come out to be 1.0. Okay, you can go home and work it out. Typical problems. These are what you might see on the exam. Is I call them type 1, type 2, and type 3 problems, but most of the time I would say type 2, where the head loss is given and you're asked to calculate the flow rate in the pipe system. Here are all the variables generally involved. We have seen them all up to this point. So let's move ahead and look at some typical problems. Uh, for example, we can end up with pipes what are called in series, in parallel, and branch systems. I'll review only 3 of them here. The loop systems you can review on your own. It's in the appendix. I think we'll talk about these because these are typical simple problems that you might see in the morning exam. Here, for example, I have the equation of continuity, and I'm going to show you how to use the head loss equation, law of conservation of energy. Most of the problems involve the use of these 2 equations. In this particular problem that I've set up for you, we'll have 3 pipes in series initially, pipe 1, pipe 2, and pipe 3. The water comes out of a reservoir, and you'll be asked to calculate something, for example, the flow rate in the system. That's what I call type 2 problem. But keep in mind, in order to calculate that flow rate, you have to know the head loss, total head loss. That typically is obtained from the Bernoulli equation, the energy equation. So you'll have to use both these equations in order to solve the problems. So let me illustrate that. Before I do that, I want to show you a few things. First of all, for pipes in series, which you'll see in my example, typically the head loss is the sum of all the head loss in each pipe, but the flow rate remains the same or constant in each pipe. So QE is equal to Q1 is equal to Q2 is equal to Q3. It's constant. So what that does is it basically gives you a third equation for the K values. Remember we talked about that loss coefficient? For pipes in series, you basically add up all the K values in order to get the equivalent KE. For pipes in parallel, the head loss is constant across the parallel pipes, but the Q's kind of split up, and that leads to this equation, number 22. So if you want to take 2 parallel pipes and combine them, the equivalent pipe 1 over KE is computed using the reciprocals as shown here, equation 22. I'll illustrate both these two in my example, how to calculate the equivalent KE for these pipe systems. So in this case, what I've done is I've taken the liberty of setting up a problem for you. In the first case, number 1, the head drop from the reservoir point A to point E here, that's a free open surface. It's basically a free surface or atmospheric pressure there. At that point, the total drop is 200 feet. And the system is composed of pipes 1 and 2 and 3. And for the same system, find the discharge when the parallel pipe 4 is added on. So I'm going to calculate the discharge in this pipe that's coming out of the reservoir into this pipe for these 2 scenarios or 2 cases. So let's look at case number 1. Before I do all the case one, I have to calculate all the K values. That's step number 1. So in this case, for each pipe, I calculate K1, K2, K3. This is the loss coefficient, which is required in order to calculate the flow rate Q using the Hausen-Williams equation. So here are the K values. Make sure you go through these very carefully. For instance, K1 is 4.67 for a 12-inch pipe. It's 1,000 feet long. C is 120. So anyway, those are all the K values, including the pipe number 4, which is the fourth pipe that I'm going to add in the second part of the problem. For the pipes 1, 2, and 3, they're all in series. So the equivalent pipe is the sum of all the Ks. That's K1, K2, and K3. Gives me an equivalent KE of 7.164. And I'm going to use that KE in this head loss equation. Now remember the head loss, this has to be obtained from the Bernoulli equation. That Bernoulli equation is going to be applied from point A to point E. Now if you apply that equation, it'll simply say the head loss from A to B, A to E is 200 feet. And that is basically independently obtained from the Bernoulli equation. And then therefore, in order to solve for the flow, we simply use this equation. The head loss is equal to KE Q to the power 1.85, which is the equation that I showed you earlier for friction loss. And therefore, invert that equation to solve for Q. In this case, it comes out to be 6.05 CFS. So it's so easy to calculate the flow rate given that head loss of 200 feet. Now I'm going to add, by the way, before I do this, go to the next part of the problem, I want to talk about this equivalent KE. This is called the equivalent pipe method, by the way. Very often, let's say you want to replace these three pipes with one single pipe, then all you have to do is consider this so-called the equivalent KE for those three pipes. Now that KE, by the way, has several terms in it. It has a length in it, it has a C in it, and a pipe diameter in it. So there might be an extension to this problem or an additional question asking you what pipe would you select that has this equivalent KE. Well, in that case, you have to know the C value and you have to know the length of the pipe also. Those have to be pre-specified because there are three unknowns in that equation. So typically what we would do is in replacing these three pipes, for example, I would probably take the total length of what we have there, all the three pipes, as my equivalent length, LE. Also, since we're replacing the whole system with a new pipe, that C value will depend upon the type of pipe you're replacing it with. So that'll be your C equivalent pipe. And finally, the only unknown will be the pipe diameter, DE, of the equivalent pipe. So that's what you're going to solve for. Okay, so that is a natural extension to this problem, which I've not shown here, but they could ask you potentially. That's called the equivalent pipe method. You can do the same thing for parallel pipes also. Here I've showing you the application or use of the parallel pipe application. In this case, we still have the three pipes in series, but there's a fourth pipe here added on that's in parallel to pipe number 2. So in that case, what you want to do is first is to take these two parallel pipes and convert them into single pipe. And that KE is obtained by taking the reciprocal sum of the two pipes 2 and 4. Their K values are given right here. K2 is 4.852 and K4 is 19.697. And you take the reciprocal sum, you get a KE of 2.379. So therefore, this equivalent pipe now for those two parallel pipes is this, okay? This is essentially going to represents the same head loss as would transpire if the two parallel pipes are used. We're going to replace then the whole, once we get the parallel pipes replaced with a single pipe, that's essentially now we recognize that we have one pipe number 1 and these the equivalent pipe that I just got and pipe number 3 are in series. So we sum all their K values and the total K equivalent of the entire system, in this case 4.691. And therefore the Q can easily be obtained is 7.6 CFS. Now if you note, in the previous case, the flow rate was smaller. It was 6.05 CFS. There's a slight increase in the flow rate primarily because of the fourth pipe we just added on in the system. Okay, so that's essentially demonstrates how to handle pipes in series or pipes in parallel in such problems. I've set up a small problem for you. You can work on this again. In this case, I do give you the K values in the problem, but these are all pipes in series, so that should make it fairly easy. The first question I'm asking you is to replace, to calculate KE for a single pipe to represent these three pipes in series, 1, 2, and 3. Okay. And then I ask you for some additional information on the equivalent pipe itself, and finally the discharge from the reservoir. Okay, so you can go ahead and work on this as per my example. It's kind of similar to what we just did. Finally, I will review this. I know this might seem a little complicated problem to solve, but it seems to be quite a popular exam on this, a popular question on this exam. It's what we call a branch pipe system. And what I'm going to show you is a method that's very quick and easy to work with. And typically what it involves is essentially the following things. Uh, they give you two reservoirs or three reservoirs interconnected by pipes, and they all meet at a junction. I call it here junction J. Typically in a situation like this, we do not know the hydraulic head or the pressure at junction J. That's an internal point, and normally what we solve for is the hydraulic head at that junction J. In this problem, by the way, we have to recognize these are pipes. The velocity heads are small. So we're going to neglect any changes in velocity head. So all we're going to be working with is what we call the hydraulic head or the piezometric head, P over gamma plus Z term. Okay? And of course, we'll use the friction equation in this form, which I just talked about earlier. And the problem is that the continuity equation can take on two forms depending on which way the flow goes. For example, there are two possible scenarios. Reservoir A and B can combine to feed flow into reservoir C. So in that case, the flow coming in from pipe 1, pipe 2, add up to give you the total flow going out. Usually that's from law of mass balance or equation of continuity. But as you will see, since we do not know what the pressure head is here, or the hydraulic head is at junction J, that's the unknown, it will depend on what we assume. So the flow balance may not be satisfied initially. But instead of doing trial and error, I'll show you a method that'll give you the answer correctly. The true hydraulic head at junction J will be such that the flow coming in from these two reservoirs will be equal to flow going out into reservoir C. That's the equation of continuity is met. That's the first scenario, which is this one right here. The second scenario, I'm sorry, this is the first scenario. This is the second scenario where the reservoir B and reservoir A is feeding into both the reservoir B and C. So the flow coming in out of this reservoir is going into either of these two reservoirs combined. So that'll again depend upon the hydraulic head at junction J in this particular problem. We're going to neglect the velocity head, as I pointed out to you. And J is an internal point. As I just said, the pressure is unknown. It will never be known. And that's not what we are interested in. We're only interested in the total hydraulic head. And let's look at a problem, and that'll elaborate this further. Typically here, I've given you three reservoirs. Reservoir 1, or I call it Reservoir A, at a height of 30 meters from the datum. It's a free surface here, so the hydraulic head, P over gamma, is equal to 30 meters. Reservoir B is at an elevation of 18 meters, and Reservoir C at 9 meters. The question they're going to ask you is, what's the hydraulic head for this junction J? What should it be? That's what we have to solve for. Now, the way we do it is, of course, we'll have to do only two attempts, and then I'm going to introduce a graphical method that solves the whole problem. First, before we start, let's recognize a few things. For reservoir A, which is point 1 here, P1 over gamma plus Z1 is 30 meters. Same thing for reservoir B, which is basically this point 2 here. It's 18 meters. And reservoir C is finally 9 meters. Now keep in mind that sometimes they give you an internal pressure in one of these elevated tanks with the pressure on top. In that case, use the pressure that they give you, P1 over gamma. Don't assume it's zero, okay? So So just substitute whatever pressure that's given. So bottom line is what you have to calculate is the hydraulic head. In this case, it just happens to be equal to Z1, Z2, and Z3. That's because these are reservoirs with free surfaces. So the first thing we're going to do, here's the solution. The first thing you do is calculate all the K values. That's in all hydraulic problems, pipe problems, this is the first step always. This is in SI units, so I use the formula 10.7, length L divided by C to the power 1.85 and D to the power 4.87, all in consistent units. In this case, K1 is 3.942, K2 is 30.552, K3 is 15.812. Now remember, you have to do this computation accurately because there's no way to verify these numbers whether they're right or wrong. And once you got the K values, we're ready to solve the problem. What I suggest in step number 2 is just assume the hydraulic head at junction J initially. In this case, it doesn't matter what you assume. 20 meters, I start with that. That basically puts me between reservoir A, which is, remember, is 30 meters. Reservoir B is at 18 meters. So this puts me between reservoirs 1 and 2. So basically, my continuity equation should say flow coming in out of reservoir 1 must go into flow going into reservoir 2 and 3 combined. Let's see if that's true and how much we're off by that, by assuming this particular hydraulic junction head. So for example, in pipe number 1, the head loss will obviously be, if you apply the Bernoulli equation between 1 and the junction J, neglecting the velocity head, it's P over gamma plus Z, P1 over gamma plus Z1 minus P2, Pj over gamma plus Zj will give you 10 meters head loss. And that's expected because the total head at A is 30, the total head at junction J, the assumed one, is 20, the difference is 10. And that has got to be equal to the head loss. So that's how you apply the Bernoulli equation to get that head loss. And once you know the head loss, you can calculate the flow, obviously. Before I do that, I also do that for reservoir 2, for pipe number 2 here, and pipe number 3 also. And there are the values, 2 meters head loss for pipe number 2, and 11 meters for pipe number 3, which is from flow from J to C, reservoir C. Once I get those head losses, I can calculate the flows. For example, the flow in pipe 1 is the head loss of 10 meters divided by the K value for that pipe, and then invert it. This is using the KQ to the power of 1.85 equation. I solve for Q. In this case, it is 1.654 meter cube per second. Do the same thing for pipe number 2 and 3. Now keep in mind, as I go along, I label them. This is the inflow into the junction. These two are outflows. If you remember, I assume the hydraulic head for junction J above reservoir number 2. So therefore, the flow has to go from the junction into the reservoir number 2. And that's why it's an outflow. Anyway, the difference between the two inflows and outflows is I call the deficit. In this case, there's a 0.604 meter cube per second of positive deficit, which means I assume basically more inflow coming in and less outflow going out. Don't worry about it at this point. What you do is move on, just call it delta 1, the deficit, and then may do one more assumption. In this case, you repeat all the steps we just did for another hydraulic head at junction J. In this case, let's say 15 meters. And if you do 15 meters, head loss in pipe number 1 will be essentially repeating the same steps, 30 minus 15, and that'll give 15 meters head loss. Once again, remember, assuming this at 15 meters, that's the hydraulic head at the junction. Remember, reservoir B is at 18. So therefore, in this case, the flow from reservoir A and B is feeding into reservoir C. So when I calculate the flows, I will show you how to handle that part. But in this case, let's do the head losses first. Head loss in pipe number 1 is 15 meters, 3 in 2, and 6 in pipe number 3. And that comes from directly from the assumed hydraulic head at junction J, which is of 15 meters. Now, then you calculate the flows like we did before. Q1 is 2.059. That's an inflow. So is Q2. Remember, we assumed the hydraulic head at junction J 15 meters to be below reservoir B. So the flow has to come out of reservoir B. That's basically what we call inflow into junction J. So those first two are inflows. The last one is an outflow. And if you take the difference of inflows minus outflow, you still get a positive deficit. In fact, this is worse than what I started off with. But it doesn't matter because the graphical method I'm going to show you will quickly give you the correct value or balance the system out. So delta 2 is 1.752. So go to the next slide. This is the key thing to do here now, is to plot the flow deficit. Remember, it can be positive or negative, so make sure you have positive or plus minus capability on your axes. And then on the horizontal axis, you have the assumed hydraulic grade at junction J. So I've plotted the 2 points for you right here. And once you join those 2 points and extend it to this point on the horizontal axis where the flow deficit is 0, will give you the correct answer to the problem, which in this case is 23 meters. Okay, so this is a graphical method of quickly converging onto the true solution. Okay, I hope if you have any questions, you can send me an email. Finally, let me just review a few things in groundwater in open channel systems, and then we'll wrap it up. As I said, there is an index, a variable that we often use in open channel systems to define the state of flow. For example, I'm sure you have heard of what we call subcritical flow, supercritical flow, and so on in open channel systems. And that's defined by a thing called the Froude number. In pipe systems, of course, you heard something called the Reynolds number, which is what we use to define turbulent flow versus laminar flow. In the case of open channel systems, we use what is called the Froude number. And Froude number is, original definition is velocity divided by square root of the G times D, the hydraulic depth, which is, I defined to you earlier. I'll repeat it again here, is the flow area divided by the top width. But in any case, I suggest you remember this equation in the final form for the Froude number is in terms of Q, because most of the problems they'll give you the discharge is Q over square root of GA cube over T. G is the acceleration due to gravity, and A cube is the flow area, and T is the top width. Uh, so we will then show you through an example how to calculate this Froude number. It's fairly easy. But in the problem in the morning exam, they probably give you a rectangular channel, which makes it even easier to calculate this Froude number. But you've got to know the definition and how to calculate it. All right, so having given you these equations, let's see what happens for a rectangular channel. This is a special case, as I said. We start with V over square root of GD. And in this case, the hydraulic depth for a rectangular channel turns out to be equal to the flow depth. Reason being, the flow area is By divided by the top width is bottom width B, so B cancels out, and you get basically V over square root of Gy, which can also be written in terms of discharge per unit width, which is Q over square root of Gy cubed. So that's the best way, quickest way to calculate the Froude number in a rectangular channel system. To give you an example, here's the flow rate Q in this channel. The bottom width is 20, and the depth is 5 feet. What I would like to know is this subcritical flow or supercritical flow? In order to do that, we need to calculate the Froude number based on this information. The discharge per unit width is 400 divided by 20 or 20 CFS per foot in this example. And the Froude number, remember, is given right here. Discharge per unit width is Q, which is 20, divided by G, 32.2, times Y, which is 5 feet cubed. Don't forget to take the square root of that, and you get essentially the ratio will come out to be 0.32. If any Froude number less than 1 is subcritical flow. If it's equal to 1, it's critical flow. Anything greater than 1, it's supercritical flow. Basically, this is an important indicator of the type of flow you have in a particular channel system. Most design work, when we do design, we like to keep it subcritical flow, if at all possible. That is normally associated with smaller velocities and larger depths. So anyway, that's essentially the Froude number. There are two other components that you might see a problem in the morning exam is to calculate a critical depth in what we call an open channel flow system, and also another depth called the uniform flow depth, which we'll talk about next. Those are the two types of depths that it's good to know how to calculate them. In a rectangular channel, there's an easier way to do this, by the way, because critical flow happens when you have fluid number is equal to 1. So we can use that condition to calculate the critical depth directly, analytically. But the analytical method I have given you involves, at least for any other channel cross-section, involves the trial and error method. I've included that in the appendix. Uh, the quickest way to do is this graphical method is to use a design chart. And we'll do that. I'll emphasize that method for both the critical depth and the uniform flow depth in this particular session. So let's look at how to use this design chart. I'll do that through an example, and because most of you are not familiar with a lot of the theory behind it, but basically by equating the fluid number equal to 1, which is equation 24 here, which is in terms of discharge, what I can do is take this equation and separate it into the cross-sectional area and top width, which is both functions of depth, which is unknown, and keep the knowns on the right-hand side, which is the flow rate, Q. So basically, that thing is called the section factor in critical flow, ZC. So yeah, all you have to do is calculate ZC for me as a function of Q, and then I'll show you how to use the chart. We'll make that dimensionless, and then use the chart to calculate the critical depth. Just a special case before I show you an example on how to do that is for rectangular channel. As I said, for rectangular channel, there is a direct equation. You can directly solve for YC using Q squared over GY cubed equal to 1, which is Q squared over G. By the way, that alpha is 1 if it's not given, to the power 1/3 will give you the critical depth directly. Let me show you an example in general. Unfortunately, that won't be the case. We'll have to use a graph like this. And through the example, I'll show you how to use this chart. By the way, just to show you what this chart is all about, on the horizontal axis right here is the ratio of Z, that section factor I just told you about, ZC, to the power B to the power 2.5. That just scales it, by the way, to make it dimensionless. On the bottom is for circular, and for the top it's for trapezoidal or any other cross sections like rectangular. And now, of course, the answer we're looking for is on the vertical axis here, which gives you the ratio of the flow depth to the bottom width, Y over B ratio. Once you get that, you can calculate the depth. So I'll do this through an example, how to use this design chart. In this case, I'm asked you to compute the critical depth and velocity in a trapezoidal channel carrying a discharge of 400 CFS. The channel has a bottom width of 20 feet, slope of 2 horizontal to 1 vertical. That's the side slopes. And I'm assuming alpha is equal to 1 in this problem. 1.1, sorry. Otherwise, it'll be, if it's not given, just assume 1. The first thing you'll do in step number 1 is to calculate that critical section factor ZC, which from that equation is Q over square root of G over alpha. That's 400 divided by 32.2 divided by 1.1. By the way, there's a division sign missing right here, so make sure you put that. That's 400 divided by 32.2 divided by 1.1 to the power half, 0.5, which gives you 73.93. This is referred to as a section factor in critical flow. Then we make that dimensionless by dividing by B to the power 2.5. That's the only reason I do step number 2. Divide by 20 to the power 2.5, which is 20 is the bottom width. The given bottom width is 20 feet, by the way, right here. And that gives you 0.0413. Now, I'm going to go with this ratio to that chart. So for a moment, I'll take you back to the previous slide, and then we'll read from that y of b equal to 0.11. Now, keep in mind, in this problem, I've given you a trapezoidal channel with a side slope of 2. So if I go back to the previous slide with a ratio of 0.0413, now I've done some additional markings for you to guide you through this, but 0.04 marking is right there somewhere. It's kind of hard to read this chart, so you might want to print it out or something before you look at it. But basically, it's right that line, close to it. So just come down all the way to z of 2. They all merge here, these curves. Z of 2 is basically shown labeled as this curve right there. So if you bring it down to this stage as with 0.04 right there, will be somewhere at this point. So that's, if you go across, we're talking about like 0.11, and that's what I have read from that chart for this particular problem, y over b of 0.11. So now the yc then is obtained by multiplying that with b. That's 2.22 feet is the critical depth. Now, if you're not sure if you did this calculation correctly or not, what I suggest is calculate the Froude number, and that should be equal to 1. So q squared over gy cubed for this is a trapezoidal channel, so you have to be a little careful. You have to do q squared t over ga cubed equal to 1. That means you have to calculate the top width and, of course, the flow area for a depth of 2.22 feet before you can proceed to calculate the Froude number. Now, the next thing is I'll talk about is computation of what we call uniform flow depth, which is the normal depth. The only reason I'm even bringing this up is because many channel systems we design using this depth. Of course, that part of the discussion is for more advanced application for the afternoon participants. But in the morning session, if they do give you a small rectangular channel, a problem involving a rectangular channel and ask you to compute the normal depth or uniform flow depth, you should know how to do that. I think that we can expect at least a basic knowledge of what this depth is all about. It's also referred to as normal depth, and basically what this depth is in the channel exists when the gravitational force balance out all frictional forces. That means bottom line is when you assume the friction slope, as we'll see in the Manning's formula, equal to the channel slope, we get uniform flow depth. So depth is the same constant everywhere in the channel. That's what it means. Now, the question is how to calculate that. Typically, we use what is called the Manning's formula in open channel systems. In the US units, you probably have seen this. It's velocity, in terms of velocity, is 1.49 over Manning's n, r to the power 2/3 s naught to the power of half. That r is the hydraulic radius. S naught, notice S naught here is the pipe slope or channel slope, I'm sorry. And that is basically we're assuming it's equal to the friction slope S of F. That's the rate at which the head is lost in the channel due to friction. And the two are being equal means makes this uniform flow what it is. In terms of discharge, remember from continuity, Q is equal to VA. So one can convert this equation in terms of flow rate, because typically in most problems they'll give you discharge, not the velocity. So that's the only difference is the cross-sectional area A. Remember, all these are functions of flow depth, and that's what we're trying to solve for. So if you look at this equation, in most problems, they'll give you the Q, they'll give you the Manning's N, or you can select it from a table, the roughness coefficient for channel systems. And of course, the slope will be also given, the channel slope. So the only thing unknown will be this thing called A r to the power 2/3 right here. And we often refer to that as the section factor in uniform flow. So what I'm going to do is take equation 29 and solve for that unknown in terms of all the knowns. And then we'll use the graphical method to solve the problem, to solve for the depth. Keep in mind about this 1.49, that's in US units. In SI units, if the problem is in SI, please replace that with 1.0. So Manning's formula involves 1.0. Okay. Yes, I'm sorry about those answers were coming on in my chat box. It just froze on me for some reason. I didn't see them. So you guys were responding correctly. Yeah. Uh, so I apologize for that. I see here in my chat box that y'all were responding, so I was kind of worried there for a minute. I hope y'all are awake and listening to me. All right, good. If there are any other questions, I will take at the end of I'll go through the list here and make sure I've covered all bases after we finish this conversation here, or finish the session. Okay, so here's the Manning's formula. Again, keep in mind for US units, it's 1.49 here. And of course, for SI units, you have to make sure you substitute 1.0 for that. One of the things, this is good to review this because Manning's formula you will see not necessarily in open channel systems, but also in pipe systems. You will see this particular formula, and I hope you're familiar with it. The Manning's roughness coefficient N, I'll show you on the next slide what those values might look like. But make sure you use this with consistent units. Q in CFS, A is the cross-sectional area in square feet, hydraulic radius in feet, and of course slope is dimensionless. Typically they give you slopes like in feet per mile. Make sure you make that dimensionless like feet per feet. Those are some of the little things you need to be careful about. Now, here's the Manning's N for different types of, in this case I've given it for open channel systems, but you can imagine, remember that when you use closed conduits in stormwater management systems or urban stormwater systems, they also are made from similar materials. Like for example, finished concrete or unfinished concrete, Manning's N is 0.012 or 0.014. If they don't give it to you typically for concrete, I use like 0.015. Here's one for cast iron, riveted steel. You can see it's a little rougher. The higher the Manning's N, the rougher it is. For gravel type of system, channel, it's 0.029. So these are very, very approximate table. There are better tables in my references that you can use to get better handle on Manning's N. Anyway, once you get all that information, here's the method. The analytical method I will not do here. I've given you an example in the appendix. I would suggest you use the design chart again. So we'll go over that process. There's a separate chart like the critical depth. There's one for determining the normal depth also. Uh, Typically, this chart will give you the normal depth YN. We call it YN, by the way, unlike the critical depth YC. Basically, it requires a dimensionless number, AR to the power 2/3 divided by B to the power 8/3. Remember I mentioned about AR to the power 2/3. That's called the section factor in uniform flow. And the reason I'm dividing by B to the power 8/3 is to make it dimensionless. So I'll do this through an example. But before I do that, let me show you this chart. Again, this chart is similar to what we saw for the critical depth. By the way, I did all these extra things for this graph to make it look better, because all these additional markings were not there in the initial graph. So this makes it a little bit easier for you to read or use. If you can print it out, you can. I'm sure they don't allow loose materials, but otherwise you might have to take it as a book, in the form of a booklet or something. Some of your review manuals may already have this. But anyway, we'll do through this example, but before I get to that example, just in this particular figure, there's only one horizontal axis. There's nothing on top, like we saw in the other case. And in this case, everything is for circular and rectangular and so on. So there's your rectangular pipe cross-section. There's your circular pipe. There's also for trapezoidal with different side slopes. Let's look at an example and I'll come back to this, how to use it. So in this case, I have a trapezoidal channel. They'll give you a trapezoidal channel with the bottom width, side slope, Z of 2. By the way, the side slope in some references might be referred to as small s. Be careful. But it's basically Z horizontal, 1 vertical. That's what it means. And that's what I've shown you right here. Z is 2 to 1. Okay. So for every 2 feet across, 1 foot vertical. So that's Z. In this case is 2. S naught is 0.0016. This is the longitudinal slope, by the way, of the channel. That's the Manning's N. I'm going to give you that value here. It carries a discharge of 400 CFS. That means if a channel is carrying 400 CFS with this slope and this roughness, what should be the depth? Okay, and that depth typically is what we call uniform flow depth, YN. By the way, every channel tends to flow at that depth. That's why it's called nominal depth. Basically saying that there's something called abnormal depth, and that basically is any other depth other than normal. And I won't get into that topic here. That's too advanced for the morning session. It's often referred to as gradually varied flow. But anyway, for this particular example, we're going to do the simple uniform flow depth computation. So the first step is to calculate the section factor A to the power 2/3 from the Manning's formula. So I've rearranged the Manning's formula to bring all the knowns to one side. In this case, Manning's N Q divided by 1.49 S naught to the power of half. All that information is either given or you can get it from other sources. In this case, 0.025 is Manning's N. Q is 400 CFS. 1.49 times the slope to the power of half gives you a section factor of 167.7. Make sure you do this calculation accurately. A lot of times you forget to recognize that this represents AR to the power 2/3. And so when you calculate the dimensionless ratio right here, use the number as is. Do not take to the power 2/3 again, okay? And that's a mistake very often people make, is in computing this dimensionless ratio, they forget that this number, 167.7, already represents AR to the power 2/3. So, so in this case, basically AR to the power 2/3 divided by B to the power 8/3 is 0.0569. And for this particular side slope channel, I'll go to now slide 68. For this ratio, I will compute Y over B ratio, just like we did for the critical depth. But keep this number in mind, 0.0569. I'll go back to the previous slide here. 0.0569 is near 0.06 right here, right near this vertical line. So I'm going to go up that vertical line, basically going over 0.06 approximately, to the curve that's labeled Z of 0.2, somewhere in the middle there. And if you go across, I'm somewhere in this YOB ratio is between 0.1 and 0.2. I would say around 0.15. So, and that's basically what I have here is 0.168. And you can be a little more accurate. I'm just doing this as a demonstration here. And therefore, the normal depth is Y over B ratio times 20. B is bottom width is 20 feet. Will give you 3.36 feet. So that's how you calculate the uniform depth. Now, by the way, they might ask you further under this uniform flow depth, is the flow subcritical or supercritical? Remember we talked about the Froude number. So using this depth, Yn, you can always calculate the Froude number for any depth as V over square root of Gy. Velocity divided by square root of G times Y. Just use this depth instead of the critical depth. The Froude number will come out less than 1 if it's subcritical depth. If it's greater than 1, it's supercritical flow, okay? That means the depths are small, velocity is high. In this case, the depths are high, velocity is small. And that's an important thing to consider in most channel design systems. The reason that's important is most people don't like to design channels that carry flow with a very high velocity for safety reasons. Of course, at the same time, they don't want channels that are too deep, and therefore subcritical flow also you have to be careful when you design that. Now, before I go to some of the questions that are there in the chat box, let me just I'm going to set up a problem for you. Please solve this. In this case, how to calculate critical depth and normal depth, and of course the state of flow also. So make sure you do work this problem through. Good luck on the PE exam. And there are some references that I've included. The most important one is this by C.I.A. I heard it's back on print. If you can get your hands on it, either through your employer or wherever, please get hold of it. He does some of those graphs are clearer in the book. It's for open channel system. For water supply or pressurized pipe systems, this Wiesman's book is pretty good, water supply. I've got some additional material there. By the way, here are the answers to those problems I've set up. So try these problems, see if you can get these answers. If you still run into a problem, I'll be happy to share the detailed solution with you. There is a loop system I've included for those who want to review this called the Hardy-Cross method. So you can go ahead and do all that. Let me look at these detailed questions that some of these things I was asked. I'm sorry about this, but what happened was that my chat box I thought was nobody was answering or coming through, and unfortunately that wasn't the case. Where did you get the 1.05 from? One gentleman asked. I don't remember. Is that from, you're talking about one of the 1.85? Oh, that is the exponent in the friction loss head equation. HF KQ to the power 1.85. Well, that's an empirical equation for Haas and Williams, so it's just basically from experimental work. It's not something that you can derive it, okay? Just you have to go work with it. Okay, that's for, he's asking for basically the exponent in the friction loss equation HFF, which was, if you recall, going back to, I think those slides, quite a few slides back, uh, and that's basically what he's referring to, I hope. I'm assuming that that's the case. Yeah, here it is, this equation. Basically, this for Haas and Williams, if you remember, we talked about head loss equation due to friction as kq to the power x. Basically, one of the participants is asking, where do you get this 1.85 from? I can get for the other method, the Darcy's equation, I can get the 2. I can derive that, but not for this. This is empirically based method, and therefore it comes from the derivation of the velocity, by the way. I don't want to get into the detailed derivation, but if you basically manipulate for the head loss from the velocity, you'll get the exponent of 1.85. Now, if you go back to the previous slide on this, for the Darcy's-Weisbach method, there the x was 2. Now, this one I can get because if you remember the velocity for Haas and Williams for Darcy's-Weisbach equation is V is equal to F friction factor F L over d V squared over 2G, and that's equal to the head loss due to friction. Head loss due to friction is equal to in terms of velocity, but you can always express in terms of discharge. And if you invert it, you can manipulate that equation to get it into this form, and there you'll see the exponent is 2 because it's v squared over 2g. So that translates into q squared over 2ga squared. All right, let's see the next question here. Where do you find x in the friction equation? That's the same question I think I just answered. Uh, Next one is reservoir. They give you P on the surface. Is the pressure head P or gamma? Yes, that's true. What I said in that branch system problem, let me go to that slide. I'm sorry about this, but we got a few minutes to answer these questions. I apologize for not looking at the chat box as it should have. But anyway, in this case, let's say, for example, for this reservoir here, they give you a pressure instead of being 0. That means it's not a free surface. It's like an elevated tank. In that case, P over gamma is not 0, but it's equal to whatever the pressure in PSF divided by a specific weight of water, which is 62.43. So get that in feet and then add to Z1, okay? So in this case, my example, I'm saying P1 over gamma is 0 because it's got a free surface. Okay, let's move on to the next question. Can you explain the note? This is, I'm not sure which one this is. Can that gentleman maybe send me an email about the note? I'm not quite sure what note he's referring to. Next one is, how did you get ZJ of 20? Is that basically is referring to the same slide, I'm assuming. So let's look at this problem. I think he's referring to this junction. I'm assuming a hydraulic head in junction J as 20, and therefore, in that case, remember, I'm not assuming ZJ as 20. This one is the combined value of P over gamma plus ZJ. It's not ZJ by itself, okay? Because the J is an internal point, its pressure is not 0. While as for the reservoir point, P1 over gamma is 0. Therefore, Z1 is equal to whatever that 30 meters is. So that's 30 meters represents the elevation head, but not this 20. That 20 is the combined hydraulic head. Is that okay? All right. Does it matter where you pick the head of J? Can it be below? No, not at all. You can pick any point. In my case, I picked one above, one below. All you have to do is 2 trials, okay, in this problem. Uh, Seeing comments come in really late. What is this? I don't know what this means. Serious log? Is that yours? Okay. Is the critical flow part of Manning's exam on the exam? Well, it could be because critical depth is a very important depth in many open channel flows. Most hydraulic courses that we teach, I do cover some open channel hydraulics as a part of that first course in hydraulics. So I would expect similar questions to come on the exam. Is it faster to just check all the answers to see which gives fruit number equal to 1? I'm not sure which one you're referring to, but I don't know if that's a good idea. Oh, you're talking about if I gave you a depth and asked you to see if the flow is critical or not. Yeah, that might be one way to do it. If it's basically one of those multiple choice type things. Continuity equation for, this is the next question for pumps. I've seen that is a number of references for the exam. Continuity equation for pumps. Basically, I don't know in what context you're asking me that question. Um, can you email me a little more? I'll elaborate on that. Okay. Here's another question, slide 57, step 2. Where does the g to the power, b to the power 2.5 come from? That's a totally arbitrary choice. I think I mentioned that. That's to make it dimensionless. Let me go back to slide 57 for a minute. He's referring to, I think it's further down this way. It's under critical depth. Yeah, slide 57. Okay. This b to the power 2.5 that he's talking about is essentially when I make it dimensionless, this guy right here. Remember ZC, the units of ZC are such that you have to take the bottom width to the power 2.5 to cancel the units of ZC, okay? You can work it out, look at the dimensions, and turns out that when you raise b to the power 2.5, it makes that ratio dimensionless. That 2.5 is just for that purpose, no other reason. Uh, Next, it says, isn't slide 62, I'm not sure what that question is, though. What about slide 62? Somebody's saying isn't slide 62. Let's go to 62 for a minute. Yeah. Does this participant elaborate on what he wants to know about this slide 62? I don't have in my chat box, I didn't see the entire thing. I don't know if I'm reading the whole thing or not, but it seems to be incomplete, that inquiry. Anyway, you can send me an email if you want to know more about that. Can we take the study material in a three-hole binder? You might want to ask the PE people that or ASC people that, but I think it cannot be in a three-hole binder. I think it has to be bound solid, if I'm correct. A hardy cross method for afternoon session only, usually yes, but they might give you a simple loop problem with a simplified thing. All you have to recognize in the morning session is the sum of head loss around a loop are equal to 0. So they could give you that configuration as a part of a hydraulics question. Is the Hardy cross method on afternoon principle possible in the morning session? I just answered that in a very elementary way, probably. What about as well as Appendix B, afternoon only? Not all of it. I put some basic analytical method of solving for critical uniform flow depth. Most likely analytical methods, I don't think they allow you to take calculators where you can use them to solve trial and error problems. So if you're going to stick to the graphical method, you probably won't need to do that. On slide 64, you refer to slide 68? Is this reference correct? Let's go to slide 64. Okay. One of the participants saying I'm referring to a slide 68 with that side slope. No, this should be, thanks for pointing that out. That is, I'm referring to is the graph, which is slide 62, yes. So please make that correction. Thank you for pointing that out. That should be slide 62, and I'll make a note of it too. What is the alpha in equation 25? That takes me, this alpha is the kinetic energy correction factor. I think I talked about it. As far as you guys are concerned for the morning session, they'll either give it to you, if not, just assume it's equal to 1 in the equation. It's meant for the fact that you're using average velocity and to correct for the kinetic energy transported under those conditions. That's what it's intended for, okay? Where was I? Let's see. Do you know where I was with alpha? Okay. I'm trying to see where it was here, and then we'll quit here soon. Okay, as well as Appendix B, I've answered all these. Yeah, I've just answered this one. Next one is, what this says is, oh, I lost that. Okay, I think that's about all I've pretty much covered. You can bring a 3-ring binder so long as there are no loose sheets. Somebody's saying that. If that's true, then that's fine. Yeah, you might want to check with someone about that. A lot of people are saying it's acceptable, so that's fine. I thought the old rules didn't allow for 3-hole binders, but if that's the case, please be my... Anyway, thanks for listening, and I hope I answered all the questions finally. Sorry about that confusion. This new system doesn't show up all the chat things in a complete form. Thank you for listening, and good luck on your exam. And I'll talk to you again on Thursday. This time I'll cover another important subject.